Earth is tilted at 23.5 degrees. Every textbook says so. None of them explain why. The tilt gives us seasons, weather patterns, and climate zones. Without it, life on Earth would look completely different. So what caused it? The textbook answer is a planet-sized impact billions of years ago. The same collision thought to have created the Moon. But there's a contradiction here, and it leads somewhere unexpected. Let's start with what we know. Earth's axial tilt oscillates between about 22 and 24.5 degrees, a wobble called obliquity cycling. This is well-established Milankovitch theory, confirmed by decades of ice core data. The tilt drifts over tens of thousands of years. But here's the question nobody asks. If the Moon stabilizes Earth's tilt, why does the tilt exist at all? Planetary scientists point out that the Moon helps keep the tilt from swinging wildly, the way Mars's tilt does without a large stabilizing Moon. But the mechanism that created the tilt in the first place is a separate problem. Life thrives at the equator, where seasons barely exist. The first life appeared in oceans, where deep water temperature stays constant. We also know that Earth's magnetic pole positions have shifted over geological time. Paleomagnetic data from ocean floor basalts confirms this. The geological record shows significant polar wander spanning millions of years. Could an asteroid have done this? The crustal displacement idea suggests a massive impact could slide Earth's crust over its mantle. It sounds elegant, but the physics present real problems. The contact area between the lithosphere and the mantle is the entire surface of the Earth. The contact area of a meteorite, even 100s of kilometers wide, is negligible by comparison. The friction alone would resist any sliding. A bullet can't rotate a bulletproof vest around the mannequin. So, if you can't push the planet over and you can't slide the crust, what's left? Even if the crust did slide, it wouldn't change the axis of rotation. The planet is a gyroscope. The entire system would keep spinning around the same axis, just with the continents in different positions. This is basic angular momentum conservation. A spinning planet has two layers of gyroscopic stability. First, its own rotation around its axis. Second, its orbit around the Sun, one gyroscope inside another. To change the tilt, you'd need to overpower both. Experiments in microgravity confirm this. Cosmonauts on the ISS tried hitting spinning objects. No matter how hard you strike a gyroscope, it precesses sideways. It does not change its axis, unless the impacting mass is far greater than the gyroscope itself. So there's a real problem. No known asteroid in our solar system is massive enough to tilt a planet without destroying it entirely. Simulations of Venus-scale impacts show the axis can change, but the planet's surface gets completely melted. Earth is clearly intact. What if you don't need to hit the planet at all? What if you move the floor instead? Instead of hitting the planet, what if you change the plane it orbits on? Imagine Earth as a spinning top on a tilting table. The top keeps its angle, but relative to the new table position, its tilt has changed. Change the ecliptic plane, and every planet's axis shifts without a single impact. This is consistent with how gravitational thermodynamics. The force required to shift the ecliptic plane of an entire solar system would be immense. But look at the current state of our system. Every planet's orbit is tilted relative to the common plane. Even the Sun's own axis is tilted about 7 degrees to the ecliptic. Something influenced this system, something with enough gravitational force to bend the orbits of every planet, from Mercury to the Kuiper belt. Not a companion star, there are none within light years. One possibility worth modeling, a passing massive compact object. Think about that, every single planet in our solar system is tilted differently. If the system formed from a flat disk, why? You can't see a dormant compact object directly, but you can model its effects. So we built a simulation. We set every planet's orbit to zero inclination, zero eccentricity, zero axial tilt. A perfect solar system, fresh from the protoplanetary disk, consistent with standard formation models. Then we introduced a compact object of about 1 solar mass, passing through the system at 50 kilometers per second. That's a normal interstellar velocity. Our own Sun moves through the galaxy at roughly that speed. Rogue stellar mass objects are predicted by mainstream astrophysics. The Gaia survey has catalogued several candidates. We launched it from about 180 astronomical units out, aimed to pass close to the solar system, slightly above the ecliptic, and then we watched what the simulation produced. As it approached, Pluto's orbit shifted first, then Uranus. As the object passed through, every orbit began responding. Ecliptic planes warped, axial tilts changed across the board. A few months of gravitational chaos, and then the object was gone. Here's where it gets interesting. The simulation output matched the real solar system remarkably well. The results were consistent with reality. Inner planets like Earth, Venus, and Mars showed small orbital shifts, but the farther from the Sun, the more disruption. Outer orbits were stretched and distorted. Some simulated objects beyond Pluto ended up with orbits so elongated they resembled observed long-period comets. There's a nuance worth noting. Earth's ecliptic inclination is 7 degrees, yet the axial tilt is 23.5. The difference can be explained by time. After the object left, the Sun gradually pulled planets back toward energetically favorable orbits. The new ecliptic plane isn't the old one, but the planets, as gyroscopes, preserved memory of the original orientation. The object passed through in a matter of months and continued into interstellar space. The solar system survived, but the disruption didn't end with the passage itself. It set something else in motion. Because the object didn't just bend orbits. In the Kuiper Belt, the vast ring of ice and rock beyond Neptune, it did something more consequential. It slowed things down. And when something in orbit loses speed, it doesn't just slow down, it falls. In a stable system, every Kuiper Belt object orbits the Sun at 3 to 4.5 kilometers per second, completing one orbit every 250 to 500 years. A massive passing object's gravity, pulling from one side, would slow objects in the nearest sector. Some would slow partially, some could lose nearly all their orbital velocity. When an object in orbit loses speed, its orbit becomes elongated. The perihelion, the closest approach to the Sun, drops inward. The more speed lost, the deeper toward the Sun the object falls. Objects that lost nearly all their velocity would begin falling almost straight toward the center of the solar system. The nearest sector of the Kuiper Belt would have been captured or ejected by the passing object entirely, gone. But the flanking sectors on either side wouldn't be captured, they'd be disrupted, slowed, and now they'd have new trajectories aimed toward the inner solar system. Is there any evidence for a gap in the Kuiper Belt? Actually, there is. Minor Planet Center data shows an uneven distribution of Kuiper Belt objects, with a notable gap roughly 36 degrees wide in one sector. Astronomers generally attribute this to observational bias. The bright band of the Milky Way creates too much light interference to detect faint objects in that region. That's a reasonable explanation, but it deserves scrutiny. Radio telescopes have penetrated Venus's 90-atmosphere cloud layer and mapped its surface. They've observed straight to the galactic center through the densest star fields imaginable. If we can do that, the question of whether we can see through one spiral arm to detect Kuiper Belt objects at least deserves investigation. The inner asteroid belt between Mars and Jupiter lies in the same plane and has been thoroughly surveyed, over 500,000 objects catalogued, with no comparable Milky Way blind spot. And the belt rotates fast enough that any observational gap would shift position over time. The Kuiper Belt gap has remained consistent across 2 decades of observation. Let's put a number on it. The outermost Kuiper Belt objects move at 1.14 astronomical units per year, the innermost at 1.63. In 20 years of observation, the gap should have narrowed measurably from orbital motion alone. The persistence of the gap across multiple survey generations raises questions that the observational bias explanation doesn't fully answer. In 2006, NASA launched New Horizons specifically to study the Kuiper Belt. Its trajectory took it through this region. From beyond the belt, there's no Milky Way interference at those angles. The data from New Horizons continues to be analyzed, and the distribution question remains open. So assume, for the sake of argument, that the gap is real. What happened to the objects that weren't captured, just slowed down? Let's follow them inward. A Kuiper Belt object with zero remaining velocity would take roughly 60 years to fall to Earth's orbit, 60 years of freefall. We modeled a Kuiper Belt object at 50 astronomical units with zero velocity. The Sun began pulling it inward, slowly at first, then faster. It took roughly 60 to 65 years to reach the inner solar system, arriving at about 600 kilometers per second. This follows directly from Keplerian orbital mechanics. Not all objects would lose the same amount of speed. Some, retaining partial velocity, would enter elongated elliptical orbits. This means the debris wouldn't arrive all at once. The first wave, the fully stopped objects, would arrive in about 60 years. Then subsequent waves, each weaker and more spread out, on roughly 100-year cycles. Now trace this debris stream through the solar system. Start from the outside and work in. The evidence is written on every surface. Neptune's axis is tilted 28 degrees, similar to Mars and Earth. In our model, Neptune was likely on the far side of the Sun during the closest approach, based on its long 164-year orbital period. It would have missed the worst of any debris wave. Uranus is tilted 97 degrees, nearly on its side. In this framework, it was closest to the passing object during transit, receiving the greatest gravitational torque, but paradoxically, its 84-year orbit would have carried it away from the debris path by the time the stream arrived decades later. The standard explanation for Uranus lying on its side involves a giant impact early in solar system history, but there's a tension in that model too. Neptune, with comparable mass and its own large moons, sits at just 28 degrees. The giant impact hypothesis requires a very specific collision that only affected one of these similar planets. But there's one piece of evidence that's hard for any single planet impact model to explain. Every planet's major moons orbit in the same plane as the planet's equator. Jupiter's Galilean moons match its 3-degree tilt. Saturn's moons and rings match its 27 degrees. Uranus's moons match its 97 degrees. The moons and planets appear to have been tilted together by something external, or the moons formed after the tilting event. Now we reach Jupiter and Saturn. These two gas giants sit right in the likely path of any inward falling debris. With their enormous gravity, they'd be both the solar system's first line of defense and its biggest absorbers. Jupiter's axis tilts only 3 degrees. In our model, it was likely on the far side of the Sun during the passage, but by the time any debris wave arrived 60 years later, Jupiter would have completed 5 full orbits. It would pass through the stream multiple times, absorbing and scattering enormous quantities of material. According to core accretion models in mainstream planetary science, Jupiter's rocky core should be about 5 to 15 Earth masses, with its total mass largely determined by how much gas it captured from the solar nebula. Its current mass of 318 Earth masses is well explained by runaway gas accretion, but some researchers have noted that its total heavy element content appears higher than formation models predict. Look at Jupiter's moons. Each one tells a different chapter of the same story. Io, the innermost Galilean moon, is the most volcanically active object in the solar system. Over 400 active volcanoes. Its surface is constantly resurfacing. Mainstream science attributes this to tidal heating from Jupiter's gravity and orbital resonance with the other moons, and that explanation is well supported. Europa is covered in kilometers-thick ice over a liquid ocean. Ganymede has its own magnetic field and an ocean beneath ice. Callisto is saturated with craters. The gradient of surface damage from innermost to outermost moon is striking, with Callisto showing the most accumulated impact history. Saturn tells a similar story. Its 6 largest moons are scarred by impacts. Mimas has a crater so enormous it looks like the Death Star, and Saturn's rings are particularly interesting. They're made of nearly pure water ice, which suggests relatively recent origin. Some researchers estimate the rings may be only 100 million years old, far younger than the planet itself. Young rings around an old planet. If they formed with Saturn, they should have darkened with dust long ago. Something made them recently. Jupiter and Saturn would have absorbed and deflected a huge portion of any incoming debris. But they couldn't catch everything. Whatever got past them would have been accelerating toward the inner planets. Jupiter's gravity would also scatter passing objects sideways. This is the same gravitational slingshot mechanism NASA uses for spacecraft. Without sideways momentum, most debris would fall straight into the Sun. Jupiter's gravity would redirect fragments toward the inner planets on collision courses. As a debris stream approaches the Sun, it compresses. The inverse square law means the same amount of material fills less and less space as it converges inward. At some point between Mars and Venus, the stream would reach maximum density. Earth and Venus orbit right in this zone. And what do we see when we look at every solid surface in the inner solar system? Craters. Everywhere. We know what happened to Venus. Its surface is uniformly young, completely resurfaced by planet-wide volcanic activity. Its atmosphere is 90 times denser than Earth's, superheated to 460 degrees. It rotates backward. Venus experienced something catastrophic. Mars shows a hemisphere-spanning scar called the Borealis Basin, one of the largest confirmed impact features in the solar system. A 2008 study in Nature modeled this as a single massive impact. Its 2 moons, Phobos and Deimos, are irregularly shaped, and their origin remains debated. Mercury, despite its small size, is covered in craters from pole to pole. Our moon is the same. Every solid surface in the inner solar system bears the marks of intense bombardment. Mainstream planetary science explains this through the late heavy bombardment model, a period roughly 3.9 billion years ago when the inner solar system experienced a spike in impacts. The NICE model, developed by Gomez, Tsiganes, Morbidelli and Levison, attributes this to orbital migration of the giant planets destabilizing the asteroid belt. It's a well-regarded framework, though the timing and intensity are still debated. But where did all that mass come from? When the first wave passed the Sun at extreme velocity, solar gravity and tidal forces would begin tearing apart the larger bodies. Fragments would scatter in all directions. Orbits would shift. Some material would be flung into new planes. This would create secondary debris hitting planets from angles the original stream couldn't reach. After the first pass, surviving debris would swing back outward on elongated orbits, losing speed, then falling inward again. Each orbit would take roughly 100 to 120 years. Each return weaker, more diffuse, but the bombardment would continue for centuries. This creates a calculable schedule of recurring impacts. The material that settled into stable orbits between Mars and Jupiter would become the asteroid belt, not necessarily from a single destroyed planet, but from debris finding its gravitational equilibrium. The belt could represent just a fraction of the original mass that circularized enough to survive long term. 500,000 known objects in that belt. If they're just the fraction that survived, how much total material came through? There's another piece of evidence worth examining. Jupiter and Saturn each have over 70 small outer moons. These aren't regular satellites formed with the planet. They're captured objects and they share 2 distinctive features. First, they cluster in similar size ranges, as if fragmented under similar conditions. Second, their orbits are steeply inclined to the equatorial plane, many retrograde, confirming they weren't formed with the planet but captured from an external source. Mainstream science agrees these are captured objects. The question is what produced so many of them. Consider Haumea, a Kuiper Belt dwarf planet. It spins so fast that a day lasts under 4 hours, and its shape is flattened into an ellipsoid. Compare it with Makemake, a similar sized Kuiper Belt object rotating at 7 hours, nearly spherical. Same region, same type of object, vastly different histories. Now step back and look at the whole picture. Every anomaly we've discussed fits one pattern. Let's talk about comets. Researchers have traced multiple comet families back to show they likely originated from the breakup of larger parent bodies. Their orbits, when calculated backward, converge to common regions near Earth's orbit. Earth's periodic meteor showers are the leftover trails of these ancient fragmentations. Because comet orbits are periodic, we can calculate when debris returns. This isn't speculation, it's celestial mechanics. The same math that predicts eclipses can predict debris cycles, and those cycles show intriguing correlations with periods of elevated cratering rates on Earth and the Moon. So here is the framework. Something massive, possibly a rogue compact object, may have passed through our solar system, not necessarily billions of years ago. The timing remains an open question that deserves rigorous investigation. It would have tilted every planet's orbital plane. It would have warped the ecliptic itself. Earth's 23.5-degree tilt in this model is not from a primordial collision. It's the residual angle between where our axis was and where the ecliptic plane shifted to. The passage would have disrupted a sector of the Kuiper belt, creating a debris wave that took decades to reach the inner planets. The gas giants would have absorbed much of it, increasing their heavy element content. The inner planets would have been bombarded. Venus may have been catastrophically resurfaced. Mars was scarred. Earth survived but was changed. This framework makes testable predictions. Comet families should trace back to common origin points. Meteor showers should fall on periodic schedules matching orbital mechanics. Gas giant compositions should show excess heavy elements. Crater densities should show clustering consistent with episodic bombardment. Several of these predictions align with existing data. Mainstream science explains each of these observations separately. The Kuiper Belt gap is observational bias. Jupiter is massive due to runaway accretion. Crater density reflects billions of years. Uranus was toppled by a giant impact. Each explanation works on its own, but a single event model offers a unified alternative that connects all of them. That's worth investigating. The 23.5-degree tilt of Earth's axis may not be a frozen relic from the birth of the solar system. It could be a record of the day something massive passed through our neighborhood and rearranged the geometry of everything. The seasons we take for granted might be evidence of an event we haven't fully understood yet. And because comet orbits are periodic, this isn't just a question about the past, it's a question about the future. Some debris may still be out there, on long elliptical paths, slowly swinging back toward the sun. The question isn't just why Earth is tilted, it's what that tilt is